to first talk about network atomic solids, which carbon and silicon are both classified as these. It's a network solid that is an atomic solid containing strong directional covalent bonds to form a giant molecule. These are usually brittle and do not conduct electricity or heat very well. Two of the most important network solids are made of carbon and silicon. We kind of saw these in our lab that we did prior to this. Carbon has two forms, diamond and graphite. And these are the two typical network solids. So diamond is a crystalline structure that has just carbon at all the indices, or the lattices, that it forms, and it's a very concrete, very strong substance. Graphite, on the other hand, has the atomic bonds holding them together, the carbons in sheets, and then each sheet is connected by weak intermolecular forces. And so their difference is because of the intermolecular force happening there. And that's why graphite is a lot weaker than diamond. Graphite as a conductor, we have these two pictures. This is on page 472 in case you want to look at it. A is showing diamond and B is showing a typical metal. So the conductivity of metals is explained by the electrons that are excited from the filled energy levels to the very near empty ones. Well, when you have a separation between the filled and the empty, then it's a lot more difficult for something to conduct an electric current. And so that's why diamond is not a very good conductor, or graphite, because there's that large gap between the molecular orbitals. Some differences between graphite and diamond. This picture is on page 473 in your textbook, and it shows that the p orbitals from the carbons are joined together to make an extensive pi bonding network, which makes the sheets very strong, but the intermolecular forces holding the sheets together not as strong. So the slipperiness that is the characteristic of graphite can be explained by noting that it's very strong bonding within the carbon layers, but little bonding between the layers. So the valence electrons are all used to form the pi and sigma bonds, holding the carbons together among the layers. And so that's why it's slippery and it's easy to break apart. Silicon is another atomic network solid, but it's a little bit different. It's an important constituent of the compounds that make up the Earth's crust. It's found in a lot of rocks, sands, and soils. But the fundamental silicon-oxygen compound is called silica, which is SiO2. And that is it's a molecule that repeats itself to make up for the network solid, not just pure silicon. So there are many different types of silicates which have silicon and oxygen bonded together. This picture is based on the SiO4 with a -4 charge tetrahedral structure and how you can form them together to make a big covalent structure. Silica is seen a lot in glass, which is shown here, where when you heat up the silica and it's cooled very rapidly, it results in an amorphous solid, which we call glass. So glass is an amorphous structure because it's not crystalline like picture A is showing you. Picture A is actually a picture of quartz, which is a crystal, and then the picture B shows the glass version. So because it has lots of disorder, they sometimes add different things to make the color change of it or make the strength different in the glass. Ceramics are another type of solid that are typically made from clays, which contain silicates, and they're hardened by firing at high temperatures. So we use crucibles and evaporating dishes, which are made from ceramic. These are non-metal materials that are strong and brittle, and they resist heat very well, and they are not attacked by chemicals very well. So ceramics are very different from glass because a glass is homogeneous, non-crystalline, frozen solution, as we could call it, whereas a ceramic is a heterogeneous compound with two phases, minute crystals of silicates that are suspended in a glassy cement. The last thing to talk about are semiconductors for level 46. Recall that the large gap in diamond between the filled and empty molecular orbitals prevents the excitation of electrons to the empty molecular orbitals, so that makes diamond an insulator, meaning it doesn't conduct well. Okay, this situation is similar to silicon, but the gap is a little bit smaller. A few electrons can cross, making it called a semiconducting element or a semiconductor. At higher temperatures, the conductivity increases. So to enhance silicon, to make it a better semiconductor, we have things where you say that it is being doped with certain elements. So we have two types of conductors, a N-type semiconductor and P-type. N-type is when you are increasing the conductivity by doping it with atoms that have more valence electrons than the atoms of the host crystal. And P-type is when you dope or add in atoms that have fewer valence electrons than the host crystal. So these pictures can be found in your textbook on page 477, where N-type silicon has silicon has 4 valence electrons. And so if we're putting in some arsenic has 5 valence electrons. So N-type is adding on something with more valence electrons. B, picture B down here, is when you're adding something with less valence electrons. So they're adding boron to the mix for that one. And then the picture on the right shows the energy level diagrams for the N-type and the P-type, where for the N-type, there's excess electrons available from the donor, and so that creates more electrons to go through. And then for the B, for the P-type, there's holes because there are electrons vacant because there's less electrons there. So that's why it would also create the connection. So the last thing we need to talk about is a p-n junction, where this is where we combine our semiconductors. So a p-n junction is what's called an excellent rectifier, which is a device that produces a pulsating direct current from alternating current. So this picture kind of shows you, it's on page 478 in your textbook, that it involves the contact of a p-type to an n-type semiconductor, where in picture A, the charge carriers of the p-type region are the holes, which are the blanks, the grayish white, and the n-type regions, the carriers, are the electrons, which are the reddish pink. In picture B, it shows that no current flows, and it's reverse bias, and C shows how the current readily flows for forward bias. And you have to see that each electron crosses the boundary, leaves a hole behind, and thus the electrons in the holes move in opposite directions from each other. So, this is all about semiconductors and everything for level 46. Please refer to your checklist for what assignment problems you have.